Imagine standing under a starry sky, looking up at a distant star. Suddenly, it flickers a brief, unexpected blink. To most people, it might seem like nothing more than a trick of the eye. But to astronomers, that tiny, fleeting moment was a goldmine of information. It was a signal, a clue that something massive, something intriguing, had just passed in front of it. At first, scientists assumed it was just another gas giant, something familiar, like our neighbor Jupiter. But as they started to analyze the data, it became clear that something wasn't quite right. The object was too big to be Neptune, but too small to be Jupiter, and it was behaving in ways no one had ever expected. What they had discovered wasn't just any ordinary exoplanet, it was a super-Neptune, a type of world so rare and unusual that scientists once thought they barely existed at all. Then, in an astonishing twist, astronomers found another super-Neptune, and then another. Suddenly, a pattern began to emerge, one that was far more exciting than anyone could have imagined. But what exactly are these strange, mysterious planets? Could they be the missing link in how planets evolve, or are they something entirely new, a whole new category of exoplanets we've never even considered? The race is on to figure out what these planets mean for our understanding of the universe, and the answers could completely rewrite everything we know about how planets form. What makes these super-Neptunes so uniquely fascinating? In January 2025, a groundbreaking discovery was made in the TWA 6054 system, two super-Neptunes that defy all expectations. While astronomers had already discovered many super-Neptunes, these two planets stood out for their orbits, temperatures, densities, and their potential to offer new insights into planetary evolution. 1. Faster orbits than anything we've seen before. One of the most exciting aspects of these newly discovered super-Neptunes is the speed at which they orbit their star. While most previously discovered super-Neptunes are found in wider orbits, taking tens to hundreds of days to complete a single revolution, the planets in the TWA 6054 system are incredibly fast. TWA 654b takes just 7.5 days to orbit its star, and TWA 6054c completes its orbit in 12.5 days. These are among the fastest orbiting super-Neptunes ever found. The discovery of these super-Neptunes in a region known as the Hot Neptune Desert, a zone where very few Neptune-sized planets are typically found, adds another layer of mystery. It suggests that planets of this size either struggle to form close to their stars, or, perhaps more intriguingly, they get stripped down over time by the intense radiation from their stars. Could these extreme conditions be why so few hot Neptunes exist? It's a tantalizing question that could shift everything we thought we knew about planetary formation. 2. Temperatures that defy the norm. Most super-Neptunes discovered up until now have temperatures ranging between 500 to 1000 Kelvin, still hot by our standards, but not overly extreme. However, these two new planets, TWA 654b and TWA 6054c, are pushing the boundaries of what we thought was possible. TWA 654b is estimated to have a temperature of about 1360 Kelvin, while TWA 6054c is slightly cooler but still sizzling at 1144 Kelvin. In Celsius, that means TWA 654b is over 1000 degrees Celsius, and TWA 6054c is just shy of 900 degrees Celsius. These scorching temperatures mean that these planets are experiencing intense heat, which has major implications for their atmospheres. At such extreme temperatures, a phenomenon known as atmospheric escape becomes a serious factor. Essentially, the intense radiation from the star could strip away the outer layers of gas over time, leaving behind smaller, more rocky cores. This could help explain why we don't see many hot Neptunes around. Perhaps they started as larger, gassy planets but gradually lost their atmospheres due to their proximity to their stars. 3. odd densities and mysterious compositions. When it comes to the internal structure of these super-Neptunes, things get even more intriguing. Most super-Neptunes discovered before have a relatively standard mix of gas, ice, and possibly a rocky core, similar to the composition of Neptune in our own solar system. But TWA 654b and TWA 6054c have lower than expected densities, suggesting that their internal compositions could be very different from what we've seen in other super-Neptunes. This discovery has huge implications for planetary science. It raises the question, are these planets composed mainly of hydrogen and helium like other gas giants, or do they contain significant amounts of water vapor and other volatiles? Their lower densities might also help astronomers figure out whether they formed in their current orbits, or whether they migrated inward from much farther out in their respective solar systems. What does this discovery mean for exoplanet research? The discovery of TWA 654b and TWA 6054c represents a rare and exciting opportunity to study planets under extreme conditions. Their tight orbits, intense temperatures, and potentially unique compositions make them stand out from other known super-Neptunes. These planets could offer crucial insights into how planets form, evolve, and interact with their stars. By studying these extreme worlds, scientists hope to answer questions about planetary formation, atmospheric loss, and the long-term evolution of Neptune-like worlds in distant solar systems. They might even hold the key to understanding the very processes that shape planets like Earth. How did we find these super-Neptunes? The discovery of TWA 654b and TWA 6054c was the result of cutting-edge observation techniques that combine space-based and ground-based methods. The role of TESS and the transit method. The first clues came from TESS, Transiting Exoplanet Survey Satellite, which was launched in 2018 to find exoplanets around bright stars. TESS scans large areas of the sky, searching for tiny dips in a star's brightness caused by a planet passing in front of it. The larger the planet, the more light it blocks, making it easier to spot. The dips observed for TWA 654b and TWA 6054c were much larger than those caused by small rocky planets like Earth, suggesting that these objects were indeed super-Neptunes. Confirming the planets with the radial velocity method. Once TESS identified potential candidates, astronomers turned to ground-based telescopes for follow-up observations. Using the radial velocity method, they measured the gravitational pull of the planets on their host stars. As the planets orbit, their gravity causes the star to wobble slightly, which shifts the star's light toward the red or blue end of the spectrum, a phenomenon known as the Doppler effect. By measuring these shifts, scientists could calculate the planets' masses and confirm their status as super-Neptunes. Are these super-Neptunes just a phase? What if super-Neptunes aren't failed gas giants, but a temporary stage in the life cycle of planets, evolving into something even more unexpected? The possibility that these planets are in the midst of a transition, shifting from one type of world to another, has sparked intense debate among scientists. Are these planets just caught in the act of becoming something entirely different? Could they be evolving into smaller, rockier worlds, or something even stranger? It's a tantalizing idea that has astronomers rethinking how planets form and evolve. Why are exoplanets mostly super versions of our own? Exoplanets are often categorized as super-Earths, super-Neptunes, and hot Jupiters, but why do these superversions dominate our discoveries? The answer lies in the detection methods we use. 1. Transit method. Larger planets block more light as they pass in front of their stars, making them much easier to detect. 1. Smaller planets, like those the size of Mercury or Mars, cause only faint dips in brightness, which are often too subtle for our current instruments to capture reliably. How can we learn more about super-Neptunes? To fully understand super-Neptunes, astronomers are turning to some of the most advanced telescopes in the world. 1. James Webb Space Telescope, JWST. JWST is revolutionizing exoplanet research with its ability to observe in the infrared spectrum. 1. This allows scientists to analyze a planet's atmosphere, temperature, and composition in ways that were previously unimaginable. 1. By studying super-Neptunes in infrared, JWST can provide insights into why hot Neptunes are so rare and whether some of these planets might evolve into smaller, rocky worlds. 2. Other ground-based telescopes, the Extremely Large Telescope, ELT, set to begin operations in 2028, will give us the ability to directly image super-Neptunes, revealing details about their atmospheres and potential surface features. 2. Meanwhile, the Ariel mission, launching in 2029, will focus on studying the atmospheres of hundreds of exoplanets, including super-Neptunes, helping scientists identify patterns in their chemical composition and thermal behavior. When will we know more? JWST is already providing groundbreaking data on exoplanets, with major findings expected within the next 5 years. By the early 2030s, with the combined efforts of JWST, Ariel, and the ELT, we will have a much clearer understanding of how super-Neptunes form, evolve, and interact with their stars. The next decade promises transformative breakthroughs, offering a detailed picture of these mysterious worlds and their role in planetary systems. The future of super-Neptunes. As we continue to push the boundaries of space exploration, super-Neptunes challenge our assumptions and broaden our understanding of what's possible in the universe. These planets are unlike anything we've seen before, and the more we learn about them, the more we realize just how diverse and fascinating the universe truly is. With upcoming missions and cutting-edge technology, we are on the cusp of unveiling the mysteries of these strange worlds, potentially reshaping our view of planetary evolution and our place in the cosmos. The best is